Hey guys, now let's discuss about the time domain analysis of RL circuit. So RL series circuit it is. So it means once voltage source, this is a switch or L. So the meaning of this time domain is the response of the resistance and inductance. Nothing but voltages and currents across this resistance and voltage, how it these responses with respect to the time period. So that's why it's called time domain analysis. So when time is equal to 0, time is equal to infinity. So with respect to time, what is the response of the resistance and inductance? That is the meaning of the time response analysis of the RL series circuit. Now let us discuss with the at t is equal to 0. At t is equal to 0 means just switch is closed. So there is a switch which is controlling the input voltage to the R and inductance. So for example, if t is equal to 0 means just switch is closed. So according to the definition of the inductor, so when just S is closed, so sudden this voltage is this input voltage is applied to this resistance and inductance. So what is the inductance definition? Inductance doesn't allow the sudden change of current. So when you apply the sudden current, sudden voltage to the inductor, then it doesn't allow. So therefore, current doesn't flow in this inductor. Therefore, T I of t, I of IL at 0 plus is also 0. 0. Then at t is equal to 0 minus. 0 minus nothing but just before closing the switch. So just before closing the switch, nothing but it is a open circuit. Okay. So open circuit, obviously the current also 0. So IL also 0. So it is 0 minus nothing but just before closing the switch. And at 0 and at t is equal to 0 plus 0 plus nothing but it is sudden changing. So at t equal to 0, because the L inductor doesn't allow the sudden change in current. So therefore at t is equal to 0 and t is equal to minus 0. So in both cases the inductor currents become 0. So then when we have to find the response. So we have to find the response at t is equal to infinity. So after closing the switch to continue, so when the switch is continuously closed at t is equal to infinity time, the AC is closed. Okay, then the inductor becomes a short circuit. So inductor becomes a short circuit. So once the inductor becomes short circuited, then resistance, the remaining circuit will be like this. This is a V and this is a resistance and inductor is short circuited, right? When the circuit is short circuited, so current becomes infinity and this will be VL, nothing but a voltage across the inductor. So now what is the response of these two? So V is equal to, and this is the input voltage and the voltage across VR and VL. So when you apply the Kirchhoff voltage law, so VR, sum of the voltage drops VR plus VL is equal to input voltage, and we are finding the response of the R and L. So at t is equal to infinity time, because after t is equal to infinite time only, then we will get responses. Okay, so this is the response of the RL circuit, and simplify this equation VR plus VL. So at t is equal to infinity, we will be getting the voltages across the resistance and voltage across the inductor, that is equal to input voltage. So what is the VR? We can write I into R. And what is the voltage across the inductor? This one already we discussed. The formula voltage across the inductor is L into di by dt. So is equal to V. So when you compare the standard form, first order differential equation. So what is the first order differential equation? Di by dt plus Vi is equal to Q, right? So to convert this equation into first order differential equation, di by dt. So what is the first order differential equation? This is compare with equation number 1. This is equation number 1, and this is the first order differential equation. This is the standard form. So di by dt plus pi is equal to Q. So this is the di by dt, R by L is equal to V by L. This is the equation number 1 of RL circuit. So this equation we are comparing here. So what is the P? Ri by L. So R by L. So when you compare this P, R by L. So what is the Q? Q V by L. So this is the comparison. So di by dt R by L into I is equal to V by L. So this is the first order differential equation of RL circuit, and now we have to take the responses of. So one is natural response and one is the forced response, that is called total response. Now individually we have to find two responses. This is also called complementary function and natural response and this forced response. So now we have to find these two one by one and add to total, then you will get the total response of the RL series circuit. So now let us see this is the total response of the RL circuit. Okay, find the natural response. This is the response of a system when input is equal to 0. There is no input, then what that is called natural response. What is a forced response? This is the response of a system when input present or applied. So at t, we have what is the input here? At t is equal to infinity, we are applying voltage across the circuit. Okay, so natural response is equal to ILT. Natural response, so apply to this natural response to the input first equation. Da by dt R by L I is equal to V by R, right? So natural response. So this is the first order equation. See here, the input voltage becomes 0. So therefore, so here is equal to 0. Then A plus B is equal to 0. So this is the first order differential equation. So in natural response, INT is equal to, we can write this is the A into e power minus pt, that is equal to A into e power minus what is the P R by L into T. So this is the natural response. And then you take the forced response. Forced response I of is I of t, nothing but I forced response at t is equal to V by R. So what is the forced response? When input voltage applied at t is equal to infinity. So therefore at t is equal to infinity, and this input, what is the input? V by R. So total response is equal to, so I of ILT is equal to, and this is our the natural response plus this is the forced response. We got here natural response and the forced response V by R. So add these two. At t is equal to 0, t is equal to 0, IL is equal to 0, right? How? At t is equal to 0, inductor doesn't allow the sudden change in current. Okay. So therefore at t is equal to 0, I of L is equal to also 0. So now you have to apply those conditions in your first order differential equation. So here at t is equal to 0, and this will become 0. I of inductor current is equal to 0. And what is the first order differential equation? A into e power minus RL by 0, t is equal to 0 plus V by R. So this whole becomes 0. So A into e power 0 plus V by R. So A e power 0 nothing but 1. Okay, A into 1 plus V by R. So if you take A is equal to, it will become minus V by R. So now we got A value here. Substitute A value in the total response. So ILT is equal to A nothing but minus V by R e power minus RL by T plus V by R. So you take V by R and V by R common. Then you will get V by R into 1 minus e power minus RL by T. So this is the time domain analysis, the time response of the R and L series circuit. So this, from this equation, so we have to draw the graph. Okay, so I of LT plus Vs of T. So this is the current and this will be the time period across the inductor. Okay, what is the equation you got? IL current is equal to V by R 1 minus e power minus R by L into T. This is the time domain analysis, first order differential equation. This is when t is equal to infinity, and this is the response of the RL circuit. Okay, for this equation, if you draw the graph, so how the inductor gets charging, how the inductor is functioning. Okay, so this is the time variation from 0 to infinity. So this is the time variation from 0 to infinity, and this will be the current response across the inductor. So this is a IL. So when the inductor getting maximum current at what time? So the meaning of this graph is, so when it's getting fully charged and when it's getting fully when it's reaching maximum current. So when the inductor is reaching maximum current at what time? That is the response. Okay. So simply we can say that, so when time, we put t is equal to L by R. So if you substitute t is equal to L by R, so L by R nothing but numerator denominator, L cancel, by R get cancel. So you'll get, so the value of this one will become 0.636 into V by R. This total value is this total value becomes, when you put t is equal to L by R, this becomes 0.636 into V by R. So at t is equal to L by R, so it reaches maximum current 0.636 into VR. So we can say time constant, it's a very important definition. Time constant of RL circuit is nothing but time in which its value reaches up to 0.636 of its final value. Nothing but, so if you multiply with 100, you will get 63 percentage. So if you multiply with 100, this one, it will get 63 percentage. So that at time at which the inductor reaches 63 percentage initially. Okay, so the inductor current is equal to 63% of the V into R. So this is the time response of the RL circuit. So the when it will reaches equal to VR, nothing but, so then you have to apply t is equal to, and L by R and 2L by R and 3L by R and 4L by R, like that. So if substitute like this, and finally the time required to reach the maximum value of maximum value nothing but V by R, it is equal to V by R. So that this is the graph, and it will become 5L by R. Substitute t is equal to 5L by R, then the current reaches maximum to up to V by R. So this is the uh, time graph of the RL circuit, and so in this is very important. Time constant of RL circuit is equal to time in which its value reaches up to 63 percentage or 0.636 of its final value is called time constant. And so this is the time response, and you have just to derive the equation and draw this graph. This is enough for you, I think. So I clear all the doubts, and so I have derived the equation, all the stuff. And still, if you have any doubts, please mention in the comment section. I'll get back to you. I hope you understand. Thank you so much.